Alright, so let me write those out real quickly on here. So the derivative of that, natural log of the base, a to the power times u prime. Natural log, or log a of u, 1 over natural log u prime over u. So let's do a couple examples. For example, if we've got, instead of e to the x, we've got 7 to the x. If we want to take that derivative, it's natural log of our base. What's our base? Times our base to its power times the derivative of the exponent, which is 1. So however you want to write that, we call that 7 to the x, natural log 7. Let's see, let's do another one. Let's do that one. The key is just recognizing what formula we're using for this derivative. We have a constant base, a variable exponent, so that derivative is natural log of the base, and what's our base? 4 times our base to its exponent times the derivative of the exponent. What's the derivative of the exponent? 2x. So however you want to rearrange that, let's call that 2x 4 to the x squared minus 3 natural log of 4. Since it's all multiplied together, multiplication is commutative, we can change the order. Let's do another one. Let's do that one. What's the rule we're going to have to use? We have a product, we have something times something. We call that u, and that v is the derivative of the first one times the second one plus the first one times the derivative of the second one. So the derivative of 2 to the x is natural log of the base times 2 to the x times the derivative of the exponent, which is 1. Anything that both terms have in common, keep those both are terms. So we have a 2 to the x. Both of these have at least an x in them. So if we factor out an x times 2 to the x, we're left with a 2 in the first term. If we factor an x out of this, we're left with an x. We factor a 2 to the x out, also left with natural log. So there's really nothing significantly new here. It's just we have a new type of function, so a new formula to take its derivative. We want to take the derivative of log base 9 of x squared plus 1. The derivative of that remember, for the derivative of log, it's 1 over natural log of the base, then u prime over u. So it's 1 over natural log of our base, and what's our base? 9. And then the rest of it is just like taking the derivative of natural log. This goes on bottom. Its derivative goes on top. So what's the derivative of that? 2x. So y prime is 2x over natural log 9 times x squared plus 1. Either way, you can write it, that's fine. I'd probably leave it like that middle one there. Now we did some very similar to this Monday, except we had natural logs instead of logs. So remember that our derivative is 1 over natural log of the base times u prime over u. What is our u here? Is that whole thing? So if we leave it like it is, then we would have to take the derivative of that and then put it over itself. Well, that's going to be a little messy because the derivative of that is chain rule. So, as you said, let's rewrite that. Instead of calling it the square root, call that to the 1/2 power. We have a rational exponent. Our denominator tells us our root. If we have a log of something to a power, what can we do with that exponent? Pull that out front. Then that derivative is not quite so bad, because when we do u prime, that's just a simple polynomial. So when we take the derivative, 1/2 stays out front. It's 1 over natural log of our base, and our base is 5, times u prime over u. So u is 3x minus 1, so u prime 3. So however you want to compile that. So 3 on top, 2 natural log 5 times 3x minus 1. Let's do something kind of peculiar here. We don't have a formula to do that derivative. We have formulas when we have x to a constant power, and we have formulas when we have a constant to a variable power, but here we have a variable to a variable power. So we don't really have a formula for doing that derivative. But we've done something before called logarithmic differentiation, where we start by taking the log of both sides. Or we could even take the natural log of both sides. If we have something to power, what can we do with that exponent? So we haven't taken a derivative. All we've done is rewrite this function. We've taken it from y equals x to the x, and we took log of both sides, simplified it a little. Now we can take the derivative of both sides here. We know how to take this derivative. We know how to take that derivative. So if we take the derivative of both sides with respect to x, the derivative of the left side, y goes on bottom, and the derivative of y with respect to x is dy over dx. If we take the derivative of the right side with respect to x, what's the formula we're going to have to use? Product. We have a product of variable factors. So the derivative of the first times the second plus the first times the derivative of the second. And what's the derivative of natural log x? 1 over x. That reduces. So dy over dx all over y equals natural log x plus 1. And how do we get dy over dx by itself? Multiply both sides by y. But what is y? Yeah. Originally, we said that y is just x to the x. So instead of calling that y, that's x to the x. So we took something that we did not have a rule for taking the derivative, but we just did a little bit of algebra to move our formula around a little bit, our equation around, until we were able to come up with something that we did know how to take the derivative of. Now that's rare that we have an equation or a function that we don't have a rule for taking the derivative of. Most any function that we're going to deal with, we have a rule for taking its derivative. It could be messy, and it could be more advisable to take the natural log of both sides before we take the derivative because of properties of logarithms. For example, pulling exponents out front. If we have products and quotients, we can break it up into sums and differences. So occasionally, that's just a little trick you might want to keep in the back of your mind. The other piece of this section is the last thing we'll do. Deals with integrating. We've looked at taking the derivative of that, any random base to a variable exponent. We said that derivative is natural log of the base a to the u times u prime. So if we want to look at integrating a to the u du, 1 over natural log A times A to the U. Or sometimes you'll see that written A to the U over natural log A. Let's see. So one or two of those we want to integrate 7 to the 2x dx. That has a constant base with a variable exponent. So in order for it to fit this formula, what would we have to consider our u? 2x. So for it to fit that formula, our u would have to be 2x, which means du would have to be 2 dx. So if we want to make a couple notes, our a is that base. Our u is 2x, that's our du. So we have a to the u. We need du, so what are we missing to get our dx? 2, so if I put a 2 here, what else do I need? 1/2 out front. So that's a to the u. That is our du. So once we recognize about which formula we need, we just need to find, well, which part is our u? What do we need to make our du? Now just apply our integration formula. We have a 1/2 out front. To integrate that, that's a to the u over natural log of a. Well, our a is 7. Our u is what? 2x. We have a 2 natural log of a on bottom, so 7 plus 6. Let's do one more of those. What should we let be u? U is sine x. So what's du? Cosine x dx. So you're saying that that is our du. So this is just a, some constant, to the u power so the integral of that is 1, well, we said we could call it that way, or it's a to the u, so 2 to the sine x over natural log of our a, so natural log of 2 plus 16. And that's pretty much 5.5. So those of y'all that had me for Cal 1, that's where we left off at the end of last semester. Those of y'all that didn't have me for Cal 1, that's just an expansion on tools that you've had before when you learned how to take derivatives, learn how to take integrals. All we've done for the last 4 sections is picked up new formulas for integration and new formulas for derivatives. So, if you have any questions about any of that, don't hesitate.